Yours.
Alrighty. Afternoon, everybody. How's it going? We're surviving here, day 4, afternoon. About to hit you with some math. Hope you can stay awake for it. Okay, so my talk today is on physical layer security and some of the work that I've done with my master's at Virginia Tech. So the first part of the talk is just going to be kind of like a review of what is physical security, how does it work, why does it matter, and then the next part of the talk is going to be the design work I did in GNU Radio, and then like a demo of the system and a video. So to start off, just to introduce what is physical layer security. So this is a pretty old concept. I mean, people have been talking, low probability of intercept, low probability of detection since the 1970s. And what really has brought this back into popular research in the past decade has been the invention of MIMO, multi-input, multi-output technologies. And the idea behind a lot of the new research is some kind of collaborative effort between your intended transmitter and receiver that uses their shared channel. And so having a MIMO channel kind of allows you to have more variables to play with. So the naming convention here, if you're not already familiar, intended transmitter is called Alice, intended receiver, Bob, and an eavesdropper, Eve. The only interesting thing here, I guess, is for the MIMO setting here, we want to call our channel between Alice and Bob capital H, and our channel between Alice and Eve, G. So the research that's been done in the past decade has kind of, I like to separate it off into 3 little categories. Obfuscation through secure multi-antenna techniques, so things with arrays. Secret key generation, so using the shared channel between Alice and Bob to generate a secret key. And then using the same mechanics as the key generation, you can also do authentication. So I'll talk about those in a little bit more detail. So the work that I was been focused on is in this first area with secure multi-antenna techniques. So with these, you generally have a couple of options, and it depends on the channel information that you already are aware of. So if you just know Bob's channel and you don't know Eve's channel, you can either try to beamform to Bob, and then you get some level of security just based on the fact that you've conditioned your channel you've conditioned your transmission for Bob's channel better than Eve's channel. If you know Eve's channel, then you can just try to steer a null in Eve's channel, and that would be the zero forcing precoding. And then there's an optimization problem you can play between beamforming and zero forcing to kind of optimize the difference in the SNRs between Bob and Eve. And then the last technique, which is the one that I'll be focusing on today, is where you generate, only knowing Bob's channel and not Eve's channel, you generate noise that only Bob cannot see and anybody else but Bob can see. And you do that by putting your noise, you basically just steer a null in that generated noise towards Bob. So other areas, so if we look at key generation, so another approach that you can do is just to take that some shared characteristic between your intended communicants and then use that as a secret key. And the problems with this generally are that depending on your channel coherence time, if you're looking at things just like channel phase or the gains or something, and your coherence time is really large, and you end up having to, it takes a long time to generate a key because those things don't change very often. Another issue is you have to play a bit of a filtering game to make sure that there's inaccuracies between the measurements at your intended transmitter and receiver, that you account for those, but you also account for overlap that the eavesdropper might be able to get. So that's another area. And then using those exact same mechanics, but kind of just applying them in a different way, you can perform authentication. So you just have a trusted time period in which Alice and Bob authenticate, and they measure some shared characteristic of their channel. And then you have this kind of game where you have to constantly update that characteristic and then set some kind of threshold for, how much can this change in a given period of time? And then that will kind of exempt out any eavesdroppers that try to, or impersonators that try to like communicate with the intended receiver or the transmitter. So that's basically a high-level overview of what physical layer security research has been done. But why does this actually matter? Like, is anybody actually using physical layer security? And the straight answer is that in a standard, as far as I'm aware, nobody has adopted any physical layer security techniques that I'm looking at currently. However, there are several organizations, one of which is an EU consortium that's been doing a lot of applied research and looking to do just that in like Wi-Fi or LTE for new versions of Wi-Fi or cellular standards. There's also a lot of interest in doing this in machine-to-machine networks like Internet of Things. The main issue there is that if you have really, really large networks, doing key or certificate management is kind of burdensome, and it may be better to have a lightweight encryption scheme, and that's just kind of supplemented by a physical layer security scheme. And the cool thing about that is that you can implement these things pretty independently of each other, since the physical layer doesn't have anything to do with what a lot of the encryption that you're doing at higher layers. Okay, so a little bit of background information, just to kind of, if you have already heard this joke before, I'm sorry. So I'm going to talk a little bit about information theoretic security and MIMO, just to kind of get you into the realm of what we're working with here. So error correction coding. So this is just the idea that you're adding some redundancy in a clever way to reduce the error rate in a noisy channel. And so in this example here, this is like the simplest way you would do it. You would just repeat the bits, and then you would take a majority vote at the receiver. What Shannon made a discovery about codes where you categorize each code by its rate, or the amount of transmitted symbols you get for the total length, so it's a measure of how much redundancy you ended up having to add into the code. And so what Shannon said was, there's a rate that if you transmit lower than that rate, then you can have an infinitely small bit error rate. You just have to add that redundancy in a really clever way. So he didn't really say what way to actually do that, what coding scheme would provide this infinitely small bit error rate. However, he did give kind of a bit of intuition that was lacking at the current time. So if you look at this graph, this was what people were kind of just empirically discovering with different codes. And if you kind of look at that and you think, oh, well, if I wanted to have something that has 0-bit error rate, it seems like my coding rate is going to end up having to go to 0. So he kind of just showed you that that wasn't going to be the case, and defined an achievable region of codes just based on optimizing bit error rate and coding rate. So the reason I bring that up, so we're going to, I guess everyone in here has had a lot of experience with like communications, and the whole goal of this is to just transmit information from point A to point B. And if you guys have already done information theory, then you already know what I'm talking about here. But if you're just trying to quantify information, I found this to be kind of like a counterintuitive thing at first. So if you have a message that's longer, with more bits, it doesn't necessarily mean that it conveys more information. And so that motivates kind of a measure of information. And the measure of information ends up being something that's just inversely proportional to the probability of the outcome of whatever you're sending. So if I tell you something like, hey, the sun's going to rise tomorrow, like, no, duh, that's not going to give me any information. So this information measure is going to be close to 0. But if I tell you something remarkable, like, oh, hey, look, pi bombs worked, and my guinea radio it just works. That's pretty interesting. So that's going to convey a bit more information. Since we're looking at communication systems and we don't necessarily know the outcome of what you send before you send it, kind of like this, a deterministic signal doesn't actually carry any information. We're interested in these ensembles, which are just going to be probability distributions of, like, there's an alphabet of things that I can send you, and there are probabilities associated with them. And then we look at what's the average information in that ensemble, or in that alphabet of things that I'm sending you. So An example is if you do some like statistical analysis of like the English language, you can assign probabilities to each letter, and then you can take an average information of that and get an entropy of just a letter drawn at random from that, which is more useful when we're dealing with communications. And the reason that's important is because then we can use those entropy measures to kind of measure a mutual information transmitted from point A to point B, or between point A and point B. And that has two factors. One is this h of x term, which is just the how well did I make my message in the first place? Like, did I send you something stupid, like, sun's gonna rise tomorrow? Or did I actually, send you a lot of information in my initial message? And then that second term, that conditional entropy, that's part of the channel. So how much confusion was added by transmitting it through the noisy channel. And then you can also define this same channel capacity that Shannon was talking about in terms of trying to maximize the mutual information. So basically making your message as nicely concocted as possible so that only the channel is limiting what you can send. So all of that was just so that I could get to this slide where we talk about the same channel but in terms of a wiretap. So WYNER initially proposed this in the 70s. So it's not a very new concept. It's just been looked at a lot more in the past decade because now we have a different channel to mess around with the MIMO channels. So now we're defining things in terms of transmission rate and equivocation rate. So now instead of bit error rate, we're more concerned with this equivocation term. However, lower error probability is always good. So if we want to look at, so what is equivocation? It's just a measure of confusion at the eavesdropper. And if we go back to like trying to examine like what is the mutual information of the intended receiver and the eavesdropper, we find that equivocation is just this the second term in that mutual information that you use to kind of minimize the mutual information given to Eve. So if I have to send the same signal or the same message to both Bob and Eve in this channel. So I can't do anything to that to help me. However, if the channel itself, if Eve's channel is degraded enough, then I'm able to have a mutual information at Eve that's smaller than Bob. And so the secrecy capacity that he defines is what you get when you try to maximize the difference in mutual information between your intended receiver and an eavesdropper. And so in the same way that Shannon kind of creates a region of achievable codes in terms of their coding rates and bit error rates that result, WYNER creates a region in terms of their transmission rates and then in terms of their equivocation. So instead of looking at this in terms of bit error rate, now he's looking at it in terms of how much confusion does this cause an eavesdropper. He finds that if you maximize the equivocation, you end up having an equivocation rate that's equal to the source entropy, which if you go back to this slide, it's just saying that you want to make Eve's mutual information 0, so you're making that second term equal to the source entropy. And then he finds that, okay, well, whatever the largest rate that you can transmit while still maximizing the equivocation so that Eve doesn't see anything, Eve has 0 mutual information, that is my secrecy capacity. And so that's how he defines that. And it turns out that if you look at this for just like independent channels, Bob and Eve, that it's just the difference in capacity between your intended receiver and your eavesdropper. So now all of this is under the premise that Eve is going to have a degraded version of Bob's channel, which was later they were able to kind of work out so that they could have independent channels. But in the end, the entire goal here is to make sure that your eavesdropper has a crappier channel than your intended receiver. And then this is what can describe the secrecy that you can provide based on that SNR gap between Bob and Eve. So quick example, because I didn't really buy this. Like this was super counterintuitive to me. I didn't like the idea of there just being like, oh, well, okay, so just because your SNR is a little bit worse at your eavesdropper, that doesn't mean I can just send some information at some rate and be able to protect like a specific piece of that information. Like I felt like it was always just kind of random. It just didn't really gel with me. So I tried to like make an example here of a wiretap code that I think will kind of explain it a little better. So in this case here, what we're doing is we're just gray coding by quadrant. So we're doing 16 QAM, gray coding by quadrant, and then gray coding within each quadrant. And then we say, okay, well, these most significant 2 bits, we're going to call those our unprotected bits. They're going to be common to each quadrant. And then our least significant bits, those are going to be our protected bits, and those will be varying within each quadrant. So if you examine the case where, okay, let's say that Eve's going to have a worse channel than Bob. So in this case, we're going to quantify exactly how much worse and say that Eve can only, Eve's error vector magnitude is such that she can only demodulate QPSK. So I'm going to define that as her EVM is the size of a quadrant. And then Bob's error vector magnitude, it doesn't matter as much. It's as long as it can fit within a quarter of a quadrant so that he can demodulate the QPS or the 16 QAM, then you're good to go. And so what ends up happening here, and I'm going to explain this a little bit more, is that when Eve has to make a decision based on the coding scheme, her decision is always going to be ambiguous when it comes to the protected bits, and that kind of shows that there's the secrecy that's always going to come from this SNR gap. However, with this wiretap coding, you can kind of control like where is that being applied, and you can kind of harness the secrecy that nature is giving you here. So if you want a little bit more proof as to that ambiguous decision, I've laid it out here for you. So it's a little bit hokey, I think, because you have to make the assumption that the error vector magnitude is actually the entire quadrant. But if you examine the quadrant and you just pick a point and you try to just look at the area of what would be considered a 0 for the least significant bit here and what would be considered a 1, they're just equal. They're 50-50. So when Eve has to make a decision on either of those, her point can be wandering anywhere in her error vector magnitude, so she can't really say for certain whether or not it's a 0 or 1. In reality, you're going to be looking, I think, more at a radius, a circle with a radius of the quadrant, and so this is going to lean a little bit more towards being able to decode that information. But that's just an example that I think illustrates that type of coding. So in here, you're just trying to add redundancy for the sake of secrecy rather than redundancy for the sake of a better bit error rate. And then the cool thing here is that you can look at this, the bit rates for Bob and Eve in this example. So Bob's rate's 4 bits per symbol for 16 QAM. Eve's rates are 2 bits per symbol for QPSK. And then you take the difference, and that's 2 bits per symbol. And that's the rate of protected bits that you're able to send with this coding scheme. So this is all just kind of a toy example, but it kind of illustrates the concepts of secrecy through this SNR gap and how you can code to make sure that what you're sending is actually secure, that you can identify what you're sending that's secure. Then really quick here, so just a little bit of MIMO review. We're all, in all of my examples here, I'm going to assume flat fading. That's just because, I don't want to deal with like making each one of those entries an HFR filter, or, with some time dependence, and that's just a lot of work. So, in most of these techniques, we'll assume flat fading, and you can, obviously do like OFDM in a wider band case, and then have each of your carriers exist in a flat fading channel. So in this case here, with your channel state information is just the channel, that you're sounding to Bob and Eve. So the way that you would get your channel at Bob and Eve is Alice would send some training sequence, and then Bob would estimate his channel, and we make the assumption that Eve will also be able to use that training sequence to estimate her channel. So if Bob gets H, then Eve gets G. Likewise, if Bob sends his channel back, we also make the like worst case assumption that Bob's sending that in the clear, and so that Eve is also going to get Bob's channel. And then in the case that Eve was actually active in some way, then there might be an opportunity to estimate her channel, and that's kind of where the motivation might come from to do something like null steering towards Eve. However, I'm not making that assumption. I don't think it's as reasonable or just as applicable. So it's interesting because the secrecy measures that you can use are fundamentally tied to the channel state information that you have available. So, we've been talking about like deterministic quantities like secrecy capacity or secrecy rate, but you can only actually measure that in the case where you know the channel that Bob has and you know the channel that Eve has, and you can, take a difference. And so, in most scenarios when you're actually going to want to have some kind of metric like this, you're going to have to use some statistical metric like an ergodic rate, where you do a time average of all the possible places that Eve could be, or an outage probability. So when we look for passive eavesdroppers, we cannot actually measure a deterministic quantity. Okay, so all that was the background. Now I'm going to go over the artificial noise technique that I worked with. So the idea here is that Alice is going to transmit some noise, and we just condition it such that when you multiply that noise by the channel that Alice and Bob share, that noise goes to 0. And then we add it in, and therefore that noise cancels out when Bob receives it, and that noise doesn't cancel out to some degree when Eve sees it. So we don't know exactly how much noise Eve is getting. It's really based on her channel. And so in order to rule out cases where Eve might be in a favorable channel, we can kind of toy with this, and we can constantly change it, change like the weightings of it amongst like the multiple null spaces that exist. So there are multiple nulls that we could put in the direction of Bob. And so if we kind of time average it out, then on the average, then even if Eve happens to be in a relatively good position for one null, if we average it amongst multiple nulls, then it's less likely that she's going to have a low noise for the whole duration. And so here's a picture, because pictures are always better than math. So this is all in a line of sight case. This applies to non-line of sight, but this is kind of a good way of visualizing what we're doing. So we're sending some information pattern. Oftentimes we're just beamforming it towards Bob. And then we're also generating on top of that an artificial noise pattern, and we're steering a null towards Bob. And then here we have the same coding scheme that's applied so that we can have some secrecy associated with the technique. So the implementation part. So finally we get to a GNU radio flow graph. It's been a while. So here's the transmitter. Started off with just packing the bits, modulating the bits, and then we have implemented a transmit beamformer. So I'm doing asynchronous message passing from my receiver to estimate the channel. So a little bit of cheating because I'm not doing it over the air, but I have them both running in the same flow graph, and then they pass the channel estimates that Bob sees back to Eve, and then back to Alice, and then Alice uses those to weight a beamformer, and she also uses those to generate the artificial noise. Then I append a header, which I'll talk about in a second, that's mostly just used as a training sequence, and then match filtering, and then sending it out. So the header is pretty simple. I'm doing a 2x1 test bed. So I have two transmit antennas at Alice and one receive antenna at Bob and Eve. So to do that, I'm doing this like TDMA structure with unique words so that I can sound each of the channels. Then at the receiver here, I do some automatic gain control, time recovery, match filtering. You guys make this way too easy. Then I do frame synchronization using the unique word to figure out where I am. And then at that point, I can do a channel estimation. And then I put that in a stream tag, pass it to my blocks downstream to either pass back to Alice or do other stuff with. How did I implement the correlator? I mean, that's something you guys are probably pretty familiar with. But here I'm just kind of creating the correlator with a FIR filter. Once you do some math and you relate it back, you can just use the modulated, time-reversed, conjugated unique word, and just use that as your FIR filter. So this is the block. So all the heavy lifting is done in the FIR filter. And then the rest of this is me just trying to add a threshold in so that I can detect, when is my unique word occurring, burst tag that, and then I'm messing around here with where, because that correlation spike will occur in the middle of the unique word, and I wanted to push it to the beginning of the unique word. So that's all that's doing. Here's an example. So this is kind of gimmicky here because I have to manually adjust my threshold. And I've looked into doing some moving average filters, but it's not as clean. So I just have a manual adjustment right now. Another thing you can do with the correlator is you can also estimate the channel with it. So if you take the outputs, the complex correlation output, that's directly related to the channel gains that are applied as long as you're in flat fading. And you just kind of scale for the number of taps, or the number of bits in the unique word. So here's an example of that. So if my channel, in this case, I simulated it with a channel that was 0.2 minus 0.3J. And then I can just, as long as I have the as long as I have the correlator here kind of telling me where is my unique word happening, I can tag this position here in the output, and then I can just grab the sample wherever that occurred. And that's how I get my estimate of the channel. And then at the end here, I'm just passing that. So I put that channel estimate into a stream tag. I'm feeding that back to Bob so that they can do the transmit beamforming and the artificial noise generation based on that channel state information. Converting this to a packet vector for fun. And then I'm demuxing the header. So I'm just taking the training sequence off, demodulating, and then putting it out into a file. So what am I actually working with here? So I have a test bed with 3 X310s and a server. The main point of this, I guess, is just trying to optimize the data rate or the analog bandwidth that was available through the X310 by providing the network infrastructure, doing things at 10 gig E till you get to the server, and then at that point you can remote in at whatever connections available to you. And then also I'm using an octoclock to synchronize frequency and phase with all the X310s. And then here's just the servers and the stuff that I was working with. Oh, and this one's for me. Okay, I have a habit of forgetting the demo. Okay, so this is a demo of the artificial noise generator. So I've done all this was done over the air. So here's the transmitter. So I have this just divided into antenna 1 and antenna 2. So you can see the TDMA, unique word here. And if you go over to antenna 2, same thing, but just different time slot. Okay, so then at the receiver here, you can see I've got the channel state information tagged. I have to manually adjust the thresholds, and that's just to show you that that's a thing. And then I have a bar down here that I'll adjust to increase the artificial noise amplitude. So right now there's no artificial noise. And then as I increase the artificial noise amplitude, you can see the cluster variance or EVM of the Eve's signal starts to get worse and worse, while Bob's looks pretty unfazed. And you can even kind of see that a bit reflected in the time domain plot for Eve. I do have an issue with saturation, which you'll see here. So there's a limit to how much I can increase my noise, and I think it's about double whatever the signal power is. So yeah, so that's interesting. And then the thing that I think is pretty cool is when you look back at the transmitted plots here, your constellation diagram looks like a mess, your time domain looks like a mess, but somehow you added things up and they worked out at your intended receiver. All right, that's my demo. Okay, questions? We're here.
All right, we have questions from the audience. In the meantime, if you want to come up one and start getting mic'd. Yeah, you want to come up and put a mic on. Do we have questions from the audience? Nope. All right, thank you very much, Kevin.
All right.